And now it's my privilege to introduce the session chair for this year's Turing Award lecture. And the session chair is the legendary Amir Fnoueli, who won the Turing Award in 1996. He's a professor at the Weizmann Institute of Science in Israel and at New York University. And he received the Turing Award for seminal work introducing temporal logic into computing science and for outstanding contributions to program and system verification. And I am honored that Amir Fnoueli can be here today to chair the session. Over to you.
Okay, thank you very much for the very nice introduction. Leave it like this. Okay, so it's a great honor and privilege for me, and also personal pleasure to chair this session. And as you can see, it's an honor because this is a prominent and great occasion in which the Turing Award Committee has decided to honor and recognize the achievements of three of our best computer scientists, Ed Clarke, Emerson and Joseph Sifakis, in inventing and developing over the years the great idea of doing automatic verification. And it's not only their recognition, but also, in some sense, a celebration for all people who are interested in formal methods, because this recognizes the field as an important and prize-worthy endeavor. And it's also a personal pleasure because all three of the recipients are personal friends and colleagues of mine over the years, and it's very nice, and I'm very happy of giving the opportunity of chairing the session. So let me just very brief, even though this audience needs no introduction to the idea of verification or model checking, let me just very briefly summarize what were the achievements and what was the prize given for, and also some additional comments that I would like to make. So, of course, we all know that most computer applications are done by programs running on either a standard hardware or specialized hardware in some cases, and certainly embedded systems and reactive systems are a particular difficult and challenging type of systems for which we need to make sure that they are correct. And it's my opinion that what holds us back a little in being able to have wider and more extensive applications is not so much that the hardware is slow. Well, hardware can always be faster. That would be very nice to have. But the main obstacle is really our ability to construct in a reliable way large and complex and safety critical systems. So this is one of the remaining challenges. It has been for quite a while and will remain with us for some time to go. And the three recipients has made a very important contribution to trying to solve this problem. So a central problem, a central activity that has to be done in order to be able to construct reliable system is the question of verification. In verification, not getting into any technical details, in general we have some property that the system should satisfy, usually related to its specification or the notion of its correctness. And what we would like to ascertain or verify or establish is to make sure that all behaviors of the system, and I intentionally use the term behaviors because when we're talking about embedded systems and reactive systems, this is the main reason that we run those systems, for their ongoing and interesting behavior. So in current practice, in most of the cases, in most of the places, in industrial use, The way verification is done today is still mostly dynamic verification, which is a fancy name for testing. Let's run it on a lot of inputs under a lot of circumstances, and they hope that if there are bugs, or if we exercise the system long enough and extensively enough, we'll catch most of the bugs. But certainly this is at best an incomplete method, as we can quote Dijkstra, who was one of the contributors, main founders of the field, asking those questions. Testing can only discover the presence of bug rather than its absence. And if you want to verify a system, in particular a safety critical system, it's very important to attain completeness. Make sure that no bug escapes our attention. So, as opposed to dynamic verification or testing, formal verification just tries to obtain this completeness and guarantee that the system satisfies its specification or the desired property with mathematical certainty. Now, there has been a lot of research starting already very early in '67, but in the beginning, most of it was theoretical and relied on activities such as theorem proving. So completeness was established as well as a very high standard of rigor. However, the techniques that were suggested at the time were very highly labor intensive, required a lot of ingenuity from the user, and were not widely accessible to a lot of users. So the main seminal contribution of the three awardees that we have here today was in inventing the method, the idea of trying to do automatic formal verification, in which we actually in some way systematically explore all possible behaviors of the system. So this method is now known as model checking, and in 2007, just almost a year ago, this seminal contribution has been recognized, and these three scientists have been awarded the Turing Award for the invention of model checking. Now, in some sense, people usually refer to Turing Award as being the Nobel Prize of computer science, and I think this is a very nice analog, but there are some differences. And one of the important differences is that usually a Nobel Prize is given for a seminal and very important contribution, usually not very recent, because you want to let time pass and make sure that actually this thing, this idea has proven itself over the time. However, in some sense, I think that unlike Nobel Prize, a Turing Award requires even more, is more demanding. Well, this is a younger type of prize or award, so it may allow itself to be more stringent. So the Turing Award usually requires not only that you made a very important and seminal contribution sometime long ago, which withstood the test of time, but it's also very important and a very supporting evidence in consideration of the Turing Award decisions that the persons which were awarded continued to contribute in a serious manner. And I would like to spend the remaining 2 minutes of my time just telling you that indeed those three scientists not only suggested the original idea of automatic verification, but actually continued to lead the way and actually found a new discipline, the discipline of automatic or computer-aided verification, which is based on, to a large extent, on model checking. So I think it is not no exaggeration to say that those three scientists actually founded and led for the last 27 years or so the field of computer-aided verification. For example, Ed and Joseph were two of the founders of the very important and active annual conference of computer-aided verification, CAV, where most of the new ideas in automatic verification has been explored over the years. In addition, I can actually tell some facts about the individual contributions of each of the awardees themselves. I have to apologize to them that this is a very laconic, very telegraphic mention of some of the achievements. Certainly it's not supposed to be comprehensive, but just to point out the highlights of the contributions of each of the 3 awardees. So let me start with Ed alphabetically. And of course, Ed was very instrumental and very leading, and in almost all the important trends and new ideas that have been introduced into model checking and automatic verification. To mention some of them, he was involved and highly instrumental. He also got a shared award for that, is the introduction of symbolic model checking, which made a quantum jump in our ability to scale up and consider very large systems, together, of course, with Macmillan, who was his student, and also Ellen and Randy Bryant. Also, he was the first to say, well, this is not the only way to do model checking, and we should start looking at SAT, which currently is one of the competing methods to deal with very large, even larger systems than was possible before. He was very influential in pushing in general from hardware model checking, which was a very high success story. This is a story by itself, into what is the current challenge of automatic verification, which is software model checking. And in order to make this possible, he pushed very hard the ideas of abstraction and abstraction refinement. He introduced this methodology, which now is widely used for software verification, called the SIGAR methodology, in which you use spurious counterexamples in order to improve your abstraction. And abstraction, of course, is the only way of using model checking, which is essentially a technique applicable to finite state systems in order to deal with software verification, which essentially is the verification of infinite state systems. Continued to Ellen Emerson. Ellen Emerson made very strong contributions, very important contributions on the theoretical side. He was responsible for introducing to us the maximal expressive temporal logic of CTL star, and also suggested some methods by which this complicated logic could be verified. He also taught us a lot about how we can use the mu calculus in order both as a specification language as well as a very strong verification technique. This is used now everywhere in verification and also in the new field, emerging field of program synthesis or system synthesis, where the mu calculus is the main tool that people use in order to solve games and similar questions. Finally, Joseph Sifakis investigated many topics that helped us again to deal with larger systems as well as more realistic models, because the original models on which model checking, called model, was designed were models in which real time was not very explicit. We could not measure time, and what Joseph helped us a lot with is forming the models of real-time systems with their verification, joint with some other researchers as well, and he was very helpful and leading in the topic of hybrid system. More recently, he started looking at alternative ways of constructing correct system, correct by construction, and component-based program development. He is now the leader of the ARTIST Network of Excellence, which concentrates on embedded systems and new ways of constructing correct systems. Let me take no more of your time. In summary, those three awardees made a very important and seminal contribution to the state of the art. They actually formed and molded the field for 27 years. And since then, they have consistently continued to lead and make a lot of breakthrough in the development. So these remarkable achievements have been justly recognized by conferring upon them the prestigious ACM Turing Award, which we celebrate today, and all of their friends and admirers. that I consider myself to be one of them, congratulate the three recipients for this well-deserved distinguished award and wish them many more years of fruitful and constructive research. Okay, thank you very much. And I think that next we would like to look at a short video of actually recapturing the event of the Turing Award celebration itself. So if we can have the video, please.
In 1938, Alan Matheson Turing launched the modern computer era with his classic paper on computable numbers. From then on, his ideas would have tremendous influence on the development of computing, an influence that continues to this day. After receiving his PhD in mathematics from Princeton University, he returned to England to become a fellow at King's College. With the outbreak of World War II, he served Great Britain in its government code and cipher school. There he played a key role in breaking the German Enigma codes, which was instrumental in bringing about an Allied victory. In 1945, he led the team that designed and built the Automatic Computing Engine, or ACE, an important early electronic digital computer. Several of his papers are now widely acknowledged as the foundation of research in artificial intelligence. He developed the criterion known as the Turing test, his proposed method to determine whether or not a machine could actually think. Today it remains the measure of artificial intelligence. In 1966, the Association for Computing Machinery instituted the Turing Award to honor the memory of Alan Turing. Over the years, it has become universally recognized as computing's most prestigious award, given each year to individuals selected for making contributions of lasting major technical importance to the computing community. All of us owe a tremendous debt to Alan Turing. It was his originality and vision that helped make the computer revolution possible.
Financial support for the ACM A.M. Turing Award is provided by Intel Corporation and by Google.
Okay. It's a great privilege for me to introduce the first of the speakers. Again, going alphabetically. Ed Clarke, please.
Okay. Oh, great. First of all, I would like to thank ACM for this incredible award. It has indeed been quite an amazing year since it was announced last February. I would also like to thank ES Week and MSoft for hosting our talks. I can't think of a better conference for us to where we should present this material. And I would also like to thank Amir Penwelly for his kind introduction. Of course, without his seminal 1977 paper, we would not be here today talking about model checking temporal logic specifications. Model checking is an automatic verification technique. It has been used successfully to verify communications protocols and hardware designs, and it is beginning to be used for software verification as well. The main disadvantage of model checking is the state explosion phenomenon, which I suspect many of you know quite well and have suffered from. It has been my quest over the past 27 years, and it really indeed has been a quest to develop new ways of combating this this problem. As you will see, we have indeed made some progress on the problem, but it's always going to be with us, and we have to continue to find new and better ways of scaling up the power of model checking. Now, to give you some idea of what model checking can do, I want to start with an example. It's an old example, but some of you may still remember it. It was the floating point division error in the very first Pentium, the Pentium 1, in 1994. Intel used an SRT division algorithm for floating point division in the Pentium, and there were 5 entries in a table that were missing and led to this error. Now, hardware bugs are particularly troublesome because quite frequently you can't just send out a software patch, you actually have to replace the chip. And it's estimated to have cost Intel $400 to $500 million to fix this problem. Soon after Intel made the announcement that there was a real problem with the Pentium 1 chip, a former CMU student who had taken one of my classes, Manpreet Kaira, and who was then working at Intel, called me up and said, "Send me one of your students." And I sent him Zhurong Zhao, who was my best student at the time. Zhurong spent 3 or 4 months at Intel and was able to show that his thesis topic, word-level model checking, could indeed have found the Pentium error, and moreover, he was able to show that the fix that Intel came up with did indeed fix the problem. Now, unfortunately, or perhaps fortunately for those of us in the verification business, hardware errors continue to occur. Just last year, there was apparently a problem with the translation look-aside buffer in an AMD processor. It actually delayed the release date of the processor from what I have been able to learn. AMD didn't officially announce this, so I have put 2 question marks here to indicate that this is really a rumor. But if you Google AMD Barcelona bug, those of you who have your laptops with you, you can find plenty of discussion about this particular problem. Model checking. The model checking is an automatic verification technique. It was originally developed for reasoning about finite state concurrent systems. It was developed independently by Alan Emerson and myself, and by Kell and Sifakis at the university, who were then at the University of Grenoble. I think that it was truly independent discovery of an important concept. Our paper was published in Springer Lecture Notes 131, and I think theirs was published in Springer Lecture Notes 137, something like that. So they certainly deserve equal credit for the work. The techniques were also quite similar. The specifications in model checking are written in propositional temporal logic. Propositional temporal logic, as most of you know, is a notation for reasoning about the ordering of events in time without introducing time explicitly. It was first used for specifying concurrent programs by Amir Penwelly in his 1977 paper. The verification procedure is the basic idea is really quite trivial. It's an intelligent, exhaustive search of the state space to determine if the formula holds. But we've had to play some tricks over the years to scale the technique up. Model checking has a number of advantages over other approaches to verification. First of all, you don't have to construct a proof. Model checking is algorithmic. It's not deductive in nature. When it's applicable, it's usually fast compared to other rigorous techniques like interactive theorem proving, which may require months of working with a proof checker to prove a relatively simple program correct. If the specification is not satisfied, the model checker will produce a diagnostic counterexample that shows why the specification is not correct. There's no problem with partial specifications. You don't have to completely specify the system before you can begin to get useful information about its correctness. And the logics can express many of the properties that you need for reasoning about concurrent systems. It's probably the most important feature, in my opinion, is the counterexample feature. It's impossible to overestimate the importance of this feature. Some people use model checkers just to get good counterexamples for obscure errors in their designs. A counterexample trace can take you right to the source of some very obscure bug. Now, the state explosion problem is easy to understand. A 2-bit counter has 4 states. And, of course, we all know that an n-bit counter has 2 to the n states. The state explosion problem can also occur because of process interleaving. If we have 2 parallel processes, then their asynchronous composition will have 9 states. In general, if we have m processes each with n states, then their parallel composition will have n to the m states. The state explosion problem, it's possible to show that using simple complexity theoretic arguments that it's unavoidable in worst case. There's nothing you can really do about it in worst case. But we have been optimistic over the years and have made steady progress on this problem by using clever algorithms, sophisticated data structures, and good engineering. Now, there are 2 types of temporal logic. Linear temporal logic, which determines paths on infinite traces. Formulas are formed from atomic propositions, Boolean operations, and temporal operators. The proposition A will hold of a trace if A labels the first state of the trace. XA will hold of a trace if A holds at the next state on the trace. FA will hold of a trace if A holds at some point in the future on that trace. And GA will hold if A holds globally along the trace. A until B holds on the trace if A holds until a state is reached where B holds. Now, sometimes it's convenient to think of time as having a branching structure. If we have a little finite state machine like the one on the left, we can at least imagine, we don't actually do this in practice, but we can imagine fixing one state as the start state and then unwinding the label state transition graph into an infinite computation tree. Probably the most widely used branching time logic is CTL. Each operator in CTL consists of 2 parts, a path quantifier that quantifies over the paths that start at a given state, and a temporal operator that describes the behavior along a path. The formula, or the operator EFG, will hold at the root of this computation tree because there exists a path, that's the E, and at some point on the path, G holds. We would say, in this case, that G will possibly become true, or that a state label with G is reachable. AFG will hold at the root of this computation tree because along every path, that's the A, G holds at some point in the future. We would say that G is inevitable in this case, or that G will necessarily become true. AG little g will hold the root of this computation tree because along every path, G holds globally. We would say that G is an invariant, or that G holds at every reachable state. EG little g will be true at the root of this computation tree because there exists a path and G holds globally along that path. It's possible for G to hold forever. G is potentially an invariant. Now, CTL uses the four operators that I just described, plus universal and existential versions of the next time operator, and universal and existential versions of the until operator. CTL star is a more expressive logic that allows richer types of nestings of the temporal operators and can express both branching time and linear time properties. The model checking problem is really easy to state and to understand. If we have a state transition graph and a specification in temporal logic, then the model checking problem is to find all of those states S of M where the formula is true. The double turnstile means true at state S of structure M. Now, model checking algorithms were given back in the 80s for CTL, LTL, CTL star. Automata theoretic model checking algorithms were given that are still quite often used for LTL. One algorithm that was developed by myself, Alan Emerson, and Prasad Sisla even had complexity that was linear in the size of the model and in the size of the formula, linear in their product. Although the algorithm had linear complexity, it was of limited usefulness in practice because of the state explosion problem. Often the models would be so big that they wouldn't fit in the memory of the computer. Now, to give you an idea of how model checking might be used, let's suppose that you've developed a new microwave oven. I'm sure that most of you know much more about about the uses of model checking, but this is I'm not going to assume that any prior knowledge about model checking in this lecture. And let's suppose that for the microwave oven we have this controller, this finite state controller for the microwave oven. Then one property that we'd like to have the oven satisfy is that it doesn't heat up until the door is closed. We don't want anybody to get burned. Well, we can express that a little bit more concisely as not heat up until door closed. And that maps directly into temporal logic as not heat up until door closed. The tilde means not, and the U is the until operator. Now, a model checker would take this formula and would check to see that it holds over all paths in the state transition graph that I showed a couple of slides back. And it would determine if it did hold, it would tell us that the formula was true. If it didn't hold, it would give us a counterexample. Now, in model checking, we normally start with a specification. In the case if we were doing hardware verification, we would start with a specification in Verilog, VHDL, or SMV, and an informal specification in a natural language like English. We would compile the hardware description into a state transition graph, and we would transform, usually manually, the informal specification into a set of temporal logic formulas. The model checker will determine algorithmically whether the temporal logic formula is true of the transition system. And important part is to make this algorithmic check as efficient as possible. Now, in my opinion, there have been 4 big breakthroughs on the state explosion problem. The first was symbolic model checking with ordered binary decision diagrams. The first model checking algorithms used an explicit representation of the state transition graph as a linked list structure, the way that everyone tells you you're supposed to represent a graph in an algorithm text. Ken McMillan, in his first 6 weeks at CMU in 1987, came up with a much better way of representing state transition graphs and sets of states. He decided that this explicit representation was very wasteful, and that if we represented the state transition graph explicitly using binary decision diagrams, then we could check much larger systems. We implemented his algorithm. He developed the SMV model checker in his thesis. It's still widely used and can be downloaded from either Cadence or from the new SMV website. We were able to check some examples with first 10 to the 20th power reachable states, and then we even were able to check some examples with 10 to the 120th power reachable states. And it was clearly a big breakthrough. And symbolic model checking is still widely used. Another breakthrough that I had nothing to do with, but I do think was extraordinarily important, is the partial order reduction. In asynchronous systems, sometimes there will be actions that commute. For example, if we do A before B, we get the same result as if we do B before A. And when that occurs, you can use that knowledge to reduce the number of interleavings that you have to consider. I think the first one to come up with the idea of the partial order reduction was Antti Valmari, followed by Patrice Godefroy and Doron Peled. Doron's implementation using ample sets is the one that is in the spin model checker and responsible for much of its power. The next big breakthrough was bounded model checking using fast SAT solvers. Now, if I had said in 1976 when I was in graduate school that I was going to work on SAT solving for my PhD thesis, well, people would have laughed at me, and I would probably never have gotten a degree. I mean, CNF SAT was the canonical NP-complete problem, the first NP-complete problem. However, now it turns out that many CNF formulas that occur in practice can be checked for satisfiability even if they have enormous size. So some formulas that have millions of literals, millions of variables, and tens of millions of clauses can be checked for satisfiability in just a few minutes. It's now possible to handle thousands of latches rather than hundreds of latches as with OBDDs. Here's a little example of how bounded model checking works. Suppose we want to know if some property P can fail in K steps. Well, we represent the state of the system symbolically as a vector of Boolean variables. And we assume that we have a predicate I of P that will be true of a state if it's an initial state. T is the transition relation of the system, and P is the property. So this formula will be true of a path V0, V1, V2 to Vk if the path starts with an initial state. There's a transition from V0 to V1, a transition from V1 to V2, and Vk to Vk minus 1 to Vk. and the specification P is false at one of those steps. Now, we give this formula to a SAT solver, and by the way, this generalizes to all of LTL. We generalize this. We give this formula to a SAT solver, and the SAT solver will look for a satisfying instance for the variables, for the state variables V0, for the vectors of state variables V0, V1 through Vk. If it finds one, it can read off a counterexample from that assignment immediately. Now, what happens if it doesn't find one? Well, there's a little problem there. We don't know whether there aren't any counterexamples at all, and the circuit is correct. It's, P can't fail, regardless of how many steps you unwind it. Or it may be just the case that if we unwound the transition relation one more time, we unwound k plus 1 steps, we'd find a shorter, somewhat longer counterexample. Now, so that there's still work on trying to make bounded model checking complete. There are a number of techniques for determining how far you have to unwind the transition relation to be assured that if you would have encountered if there is a counterexample, you would find it by unrolling to that depth. Now, here's an example that Armin Beer sent me quite recently. It's an example of a circuit with 10,000 latches, 10,000 inputs. The formula for the problem that Armin checked had 4 million variables, 12 million clauses, and the shortest bug of length 37 was found in 69 seconds. I think that's really remarkable. We've come a long way since we were checking 10-state machines on the first model checkers. So the fourth big breakthrough is the localization reduction, or counterexample guided abstraction refinement. In 1994, Bob Kirshan wrote a book on automata theoretic verification. And there was one part in the book that I could never understand. It was his section on the localization reduction. And Bob kept telling me that it was important, but I just couldn't seem to follow all of the details. However, one of my students, Yuan Liu, became obsessed with with understanding it and finding out what was so good about it, and he managed to. He managed to figure out why the localization reduction was important. We found out that it was really not so difficult to understand at all. We generalized it, and in a way that so that it could be used with software model checkers. The original version had been written or had been developed for dealing with latches in circuits. So we had to do some work to make it to apply to programs. And it's used in most, but not all, software model checkers. Now, here's how CGAR works. We start with a program or circuit. We form a conservative over-approximation of the program or circuit, so that this abstract model has all of the behaviors of the program or circuit. Then we model check the abstract model, which presumably has far fewer states than the original program or circuit. And this can be just an off-the-shelf model checker, SMV or spin. And we can, if we don't get an error, then we know that the property holds on the original program because we are dealing with an over-approximation of the original program. If we do get an error, if we find a counterexample, then we have to check and make sure that that wasn't a trace that was introduced by the abstraction process. So we have to simulate it on the concrete model, on the original model. And if the simulation is successful and we find that it really is a bug, we can also stop. If it's not, then we want to at least eliminate that particular counterexample. So we use that information in that counterexample to refine the abstraction and loop back around the loop. And the technique is implemented in several software model checkers. I'll mention one in particular in a few minutes. A natural question to ask is it possible to go from hardware to software? Well, in Wired News in November 10th, 2005, Bill Gates announced that they were developing a software analysis tool that could find bugs in Windows device drivers, and he called it the holy grail of computer science. Now, what makes model checking software different from model checking hardware? Well, there are lots of reasons: ints, floats, strings, user-defined types and classes, pointers with aliasing, unbounded numbers of heap-allocated cells, procedure calls, recursion, calls through pointers, dynamic method lookup, overloading, concurrency with unbounded numbers of threads. I could keep going on all day. Templates, generics, include files, interrupts, exceptions, callbacks, use of secondary storage, files, databases, absent source code for libraries, system calls, mobile code, esoteric features like continuations and self-modifying code. And finally, last but not least by any means, sheer length. Microsoft Word is well over 1 million lines of code. So there has been some success in software model checking, and I think the most successful software model checker is the static device verifier that was developed at Microsoft. The same issue of Wired News that I quoted earlier, Microsoft has developed a tool called Static Device Driver that uses model checking to analyze the source code for Windows device drivers and see if the code that the programmer wrote matches a mathematical model of what a Windows device driver should do. If it doesn't, then the SDV warns that the driver might contain a bug. By the way, Microsoft claims that the reason Windows crashes so much is because of third-party device drivers. I'm a little bit skeptical myself. Now, this brings me really to the end of my talk, or almost to the end of my talk. Challenges for the future. Well, there are many. Model checking is really quite young. I think there's a lot to be done in exploiting the power of SAT. Each year there's a SAT competition, and each year the SAT solvers get faster. And they're still doubling in speed each year. Also, fast SAT solvers have made some classical decision procedures, like quantifier-free Pressburger arithmetic, feasible. You can actually use them in practice. A great deal of research on that. Compositional model checking of both hardware and software. If you have a system, it's often advantageous to break it up into parts, verify the parts separately, and then conclude something about the whole model. Now, it turns out that we've just begun to realize that the techniques that we thought worked well for compositional model checking don't work so well after all. It doesn't scale as well as we were expecting. So there's more work to be done on making compositional model checking work. Software model checking is a grand challenge problem. I don't think it will become routine in the near future. It's possible now, however, to combine model checking with static analysis techniques and find bugs in software. And there's much more to be done, though, before we can say that a piece of software is actually correct using model checking techniques. Verification of embedded systems. Well, this is actually a topic all to itself and a very important one for this conference. The best model checkers for hybrid automata for systems that have both discrete and continuous evolution governed by a differential equation can only handle a handful of variables. And that's disappointing. We really need to do something. This area is in urgent need of a breakthrough. The models seem to be good, but the techniques that have been developed so far don't scale very well. So a lot of research is needed there. Model checking and theorem proving. Well, I'm not a model checking bigot. I believe that it's important to combine model checking with other techniques, not only static analysis, but also theorem proving. The model checkers that are in some theorem proving systems, like the one in MAUD, are really quite powerful, and impressive results have been obtained. Probabilistic and statistical model checking, I think, are important. And I'm currently working on statistical model checking. It's a technique that I believe might be used to bridge the link between random testing and model checking. You can conclude something from generating a lot of traces and checking formulas on those traces. You can actually give a bound on the probability that a specification doesn't hold. Now, as the models have become so much larger, the counterexamples have grown as well. And just figuring out what's wrong with a counterexample is now, or what a counterexample is saying is a major problem. And finally, scaling up. We'll always have this problem. We'll always need to come up with better model checking techniques. Now, my own goal is to work on verification of safety-critical embedded systems. Most of you probably know that, or I'm sure all of you know, that cars are moving to drive-by-wire. I think if that happens, we'll have to verify the circuitry inside the car. And I'm almost finished, Amir. Just one more slide after this one. And I'm working with some people from GM India Science Lab on that project. Now, in this quest, in my 27-year quest, I've had a lot of help. And so I wanted to display this slide. This is a list of my PhD students, my postdocs, and my visitors over the past 27 years. And it's really been a pleasure working with them, and they are really the ones that deserve the credit for the breakthroughs that I have made.